Hello everyone, and welcome to my channel Square Wave 2. It's a nice cold rainy day here in the San Fernando Valley, Southern California. It is the end of November 2018, and I think it's a good day to do another video. So here goes. 6 years ago, I posted 3 videos showing real fun electrical toys I made for my grandson. He was 6 years old then. I had a lot of knobs, switches, bells and lights, but they were really just toys. Well, now it is 6 years later. My grandson is 12 years old, and I think he's ready for something a little more educational along electrical lines. So I built him this miniature power generating and distribution center. I built it on a piece of 1/2-inch plywood. It has a small magneto, a voltmeter, an antique telephone bell, a light bulb, and it has something up here that I call a spark gap assembly, or a spark assembly. Let's take a look at it. This is my magneto, and it's a very small one. It came out of an Army field telephone unit. It operates with just 3 horseshoe magnets. According to my voltmeter here, it will develop about 60 volts AC. Behind the magneto, I have a beautiful old antique telephone bell. It's made out of very heavy gauge steel and beautifully chrome plated. It makes a wonderful ringing sound not heard commonly for over 100 years. It's reminiscent of the days when your telephone was a big wooden box attached to the wall with a crank sticking out of the side. In the front of my unit, I have a 3-position rotary switch. Position 1 lights the lamp. Position 2 rings the antique telephone bell. What a sound! Makes me want to answer the phone. Position 3 connects my magneto over here to my voltage doubling circuit and my 3 big electrolytic capacitors. And this is wired up here to my spark gap assembly. This is what I call my spark gap assembly. It has a swinging arm with a weight at the bottom so it always returns to a vertical position. At the top of the arm is a little spike which is connected to the positive side of my capacitor bank. When I push down on the lever, the spike contacts a zinc rod or a zinc bolt which is connected to the negative side of my capacitor bank. When I push down the lever and make contact, we should get a really nice spark. I soon realized that you can't rely upon the same point of contact over and over to provide a good spark, and that is because of corrosion. So I made the arm movable to go across the length of the bolt, so you can always find a spot that works. Also keep in mind that this was designed for a 12-year-old grandson, so I wanted it to be safe. So I enclosed the spark assembly in clear plexiglass. Well, let's charge up the capacitors and see what kind of a spark we can get. Wow, that is quite a spark. I'm going to explain to my grandson that there are about 6 different ways to make electricity, beginning with friction and ending with, say, a thermocouple. However, the method of making electricity most important to us in our modern day lives is magnetic induction. This is how our giant power plants work, with magnetic induction. And the man who discovered magnetic induction was a 19th century British scientist named Michael Faraday. Faraday discovered that moving a piece of wire back and forth between the north and south poles of a magnet produced a minute electrical current in the wire. And today our massive commercial generators operate on really the same principle, but instead of a piece of wire, there are gigantic coils of wire rotating within powerful magnetic fields. And it is this very same principle that is demonstrated by my little magneto here. Here is magnetic induction on a very small scale. The magnetic part is provided by 3 horseshoe magnets here. Larger magnetos can have 5 or even up to 6 horseshoe magnets. When I turn the crank, I'm turning the large gear, which spins the small gear here, providing a speed advantage. The small gear is connected to an armature that runs this way between the north and south poles of the magnet. This armature is wound with many, many turns of fine cotton-covered wire. Yes, I did say cotton-covered wire. In those days, they didn't have the varnish-coated magnet wire we use today. The faster I spin the crank, the faster the armature spins, and the more current is induced in the winding. This is true only up to a certain point, of course. The lesson to be learned from this little magneto is that it takes energy to make electricity. There's no such thing as a free lunch. Typically, this energy comes from burning coal, oil, or natural gas to heat water to make steam, to operate steam turbines, which in turn operate the generators. Of course, atomic fission has also been used to heat the water to make the steam. And of course, the very best generator is hydroelectric, powered by water pressure, non-polluting and sustainable. But of course, this is not practical in all areas. You know, it's all too easy to imagine that our pollution problems could be solved by going all electric. But this is really not the case. Remember that the production of electricity commercially requires large amounts of energy, which may come from safe, renewable, non-polluting sources, or from very dangerous polluting sources. You know, a very progressive, forward-thinking man, like President Trump, should be doing everything in his power to discourage the use of obsolete forms of energy and encourage the production and use of new, sustainable, non-polluting forms of energy. My vote is for solar power. I think it has the greatest potential. You know, the future of our children, our grandchildren, and even the future of our very planet cannot be ignored. When I first began messing around with magnetos, I wanted to find a quick, simple way to increase the voltage output. And the first thing that came to mind, of course, was a step-up transformer. You have alternating current, and you have a turns ratio. It's a match made in heaven. It's got to work, right? Wrong. It didn't work at all. I tried every transformer in my junk box, hooked them up both ways, and either I got no voltage output or I got 1 or 2 volts. Now, at first, it didn't occur to me what the problem was. I'm sure it will occur to some of you watching what the problem was. I had to hook my magneto up to my oscilloscope and look at the waveform, and then I realized why this was not a practical idea. Up until this point, I don't think that anybody has posted a YouTube video of the waveform of a magneto, so I'm going to do it for you now. Just remember, everybody, you saw it first here on Square Wave 2.